Okay, so welcome to the next video on Structural Theory 1. So today we are going to learn the types of loadings, how it will be derived, and how it will be referred to different codes that are available locally and internationally. So as we can see here, we have types of loadings. Actually, we have dead loads, live loads, highway bridge loads, railroad bridge loads, impact loads, wind loads, snow loads, earthquake loads, hydrostatic, and soil pressure. So before we can discuss the definition of each of those loadings, let us recall the unit pressure and force. So we are going to relate now pressure and force. Previously in your strength of materials, you have encountered the unit Pascal, megapascal, or even kilopascal. So that is actually the unit for pressure. So only that in your strength of materials, it is in terms of megapascal, or simple stress is equal to P over A, isn't it? So if that is the case, that is an internal pressure. So the pressure is occurring within the body, or that is a residual pressure wherein it is termed as stress. So referring to a force pressure, of course that is an external pressure, just the same, that is equivalent to force all over area, yielding to a unit of kilonewton per square meter in SI units, and for English units it is pounds per square foot, or abbreviated as PSF. And then if we are going to cross multiply this pressure times area, we'll come up with the force is equal to pressure times area, and then as we can see by the unit itself, kilonewton per square meter multiplied by square meter, then this square meter below and above will just cancel, and finally we have a kilonewton force for that. Okay, so if you do not want to memorize the formula, just refer to the unit. In order to eliminate square meter here, just multiply it by square meter, and we all know that square meter here is a unit for area. Similarly, for English unit, PCF or PSF shall be multiplied by square foot to come up with the unit pounds in English system. So that's it. Pressure and force could be related in terms of those variables. Okay, so next we wanted to relate force and unit weight. So unit weight is defined as the ratio between weight all over the volume. This is equal to kilonewton per cubic meter in SI, and PCF or pounds per cubic feet in English system. So remember that W here is also a force, or weight is also a type of force. That is why in your formula, F is equal to mass times acceleration. Force is just replaced by W here, and then A is replaced by the acceleration due to gravity, which it is the acceleration involved in a free falling body, resulting to a force weight. Now if you are going to cross multiply now to come up with the weight is just equal to gamma times volume. So relating to the unit itself, again we wanted to eliminate cubic meter here, multiply it by cubic meter, then it is in consonance with the equation involving gamma and weight. And then doing that, cubic meter now is cancelled, then weight is derived. Okay, so this is very important in deriving the dead load. later on you will know that dead load is just a self weight of structural elements that will be included also in analysis of the structure. Okay, so if you wanted to derive any uh, material that is within the structure, of course it is so easy, because if we know the gamma, we'll just multiply it by the volume. So in most of the references we have, they have already derived gamma for almost any engineering material we wanted to use, like concrete, reinforced concrete, plain concrete, or even hollow blocks or concrete hollow blocks, uh, ceiling materials. So everything that we needed to compute for the self weight, then we can derive it by gamma volume. So in English units, just the same. PCF is now multiplied by the cubic feet in order to eliminate cubic feet at the bottom, and then we come up with the unit force W. Okay, so it's very easy, and just refer to the unit. Even if you do not know the formula, you can recall the formula by the unit itself. Okay, so by that, pressure and unit weight as a common variable, that is the force itself. So gamma is derived, or W is derived by gamma multiplying it by the volume to come up with the force, and then pressure, just multiply it by the area. Okay, by the area we will derive the force. So that connects pressure and unit weight. So weight, we would like to expand this formula, gamma times volume, and ideally if we have length times width times height here, or the surface area times the third variable is the volume also. Okay, so length times width times height could be also expressed by the combination of the length times height. Okay, so if we combine the length times height, that we will form an area. Now where is the area? It is practically on the vertical axis, multiplied by the width. Still, that is a volume. That is why gamma is equal to area times width. Or it could be that the area here is within the other side of the vertical, and then multiplying it by the length, just the same, it will yield to volume. Or it could be that the area is within the horizontal plane surface, then to make it a volume, just multiply it by the height. Okay, so why should we express a certain area here? Because that also connects to pressure, the force all over area. So again, the force is derived by multiplying pressure times area, and then force is equal to W, or force. So meaning, we'll just have to equate what we have derived from the gamma and what we have derived from pressure, because force is equivalent to force. Doing that, so this is pressure times area from the pressure formula, and then gamma volume times from the unit weight formula. So in here, two of the variables have already combined to make area, then both are present to the left and right side, so that area will just be cancelled here, and then therefore relating pressure to the gamma, we have pressure is equal to gamma times width, or it could be pressure times gamma times length, or it could be pressure is equal to gamma times height. Okay, so if you do not want to memorize that one, just refer to the, again, just refer to the unit. The unit for gamma is kilonewton per cubic meter. So you wanted to ask yourself how to make it to pressure. Of course, unit for pressure is just that the bottom variable here is the degree is reduced by 1, or square in terms of square meter. So how to do that? Just multiply it by a certain distance, okay? By a certain distance. It could be that the distance is length, or it could be the width, or it could be the height. And vice versa, if we wanted that the pressure to be converted into volume, just divide it by the third variable of the volume. Okay, it could either be width, length, or height. So I hope that is clear. Okay, so those are the basics that you need to know, because later on in a calculation of these forces, those knowledge will be essential in the derivation of the loading. Okay, now if we have converted all of those, translating it to a certain surface, we wanted to distribute it on a certain length, whether along the length, along the width, or along the height, of course. So in this case, if we have a surface pressure, remember the pressure is within the surface. Okay, we wanted to distribute to a certain dimension. So to illustrate that, if we have here a 3D structural member subjected to a pressure in terms of kilonewton per square meter, of course this length will have a certain area here, a portion of an area that this side would carry. Okay, so that is the distribution. And then for the width, just the same, there will be a certain area here that this surface, horizontal surface, will carry along the width. Now to do that, we will derive the force here, the force we will derive the resultant force by multiplying it by the area to make it in kilonewton, and then divide it by where you wanted to distribute the portion. So therefore it should be that W is equal to force all over the length. So meaning this whole pressure here is being distributed through the length. That is why the divider here is length. But to have a detail on the area, I'm just presenting it in terms of length times width to present that that is the procedure. However, as I have said, a portion of the area is distributed along the side, not the total area. So later on we will discover that one. Okay, so similarly, if we have the first and distributed load W, we wanted to distribute this pressure along the width. A while ago, the divider is the length. Now the divider should be in the side where you wanted to distribute the certain loading. Okay, again, this is an ideal instance wherein length times width, but a portion of length times width is being carried by the width, so the adjacent area usually. So again, we will discuss that on the later slides. Okay, so to have a definition of dead loads consist of the weights of the various structural members and the weights of any objects that are permanently attached to the structure. Hence, for a building, the dead loads include the weights of the column, beams, and girders, the floor slab, roofing, walls, windows, plumbing, electrical fixtures, and other miscellaneous attachments. So all of the permanent items that are attached to the building are dead loads, or simply that is the self weight. Okay, now moving on to the uh, codes. So there are available codes relating to the unit weight or minimum densities for the design loads from various materials in engineering. Okay, it could be in terms of pounds per cubic feet, or in kilonewton per cubic meter in terms of SI units. Okay, so this is table 1-2. This came from ASCE, or Association of or American Society of Civil Engineers dash SEI 7-10. So again, we have another table here, table 1-3, minimum design dead loads. This time it is in terms of pressure or kilonewton per square meter. So all of these were derived through table 1-2, only that it is being multiplied by a distance, so that it will be in terms of thickness. Okay, so just like this, if we have a walls, if we have a 4 inches clay brick, it is already in a fixed size, or 4 inches. Similarly, we have 8 inches, 12 inches, so on and so forth. As well as the frame and partition walls, this now is expressed in PSF and kilonewton per square meter as well. So for the floor fill, these floor fill are actually derived from table 1-2 on the unit weight. However, it is now specified that it is in terms of per inches. Okay, so per inches, or per millimeter in English, or SI units. Likewise, we also have derived ceilings for acoustical fiberboard, plaster on tile or concrete, suspended metal, lath and gypsum plaster, asphalt shingles, fiberboard, and among others. You will find a lot of materials from National Structural Code of the Philippines, or NSCP. But for our discussion, we will just limit ourselves for the meantime to these available tables in the book of Hibbeler. So this is the dead loads. So this is the pressure, derive the force, and then how do you derive the force? Determine the area that carries by the side you wanted to distribute the W. Actually, all of these edges have distribution in it, only that we compute how it is being distributed. Say for example, this pressure is along the surface, horizontal surface here. We multiply it by the certain area covered by that this side, okay, and then divide it by the length, along the length of distribution. Okay, remember, uniform load W is in kilonewton per meter. Therefore, we obtain first the force, then divide it by the length. So that's it. Okay, so just to repeat, pressure is equal to force over area. we derive in kilonewton, and then we just divide it by the length to come up with the uniformly distributed load, or distributed load in terms of kilonewton per meter. So in English, that is pounds per feet. Okay, so let us consider this example now. As we can see here, we have the floor beam carrying a certain partition here. So this is a beam in terms of a wide flange. So the dimension of the slab is given, and as well as the dimension of the wall here. However, this problem is silent on dimension along this side. Okay, so I have just scrapped the solution from the book of Hibeler here. As we can see, concrete slab was derived through the pressure in terms of the thickness, perhaps the thickness. Okay, because 4 inches is being multiplied by the thickness as well as the width here, 6, to come up with 192. And then the plastered ceiling here is an additional loading in terms of that pressure times 6 feet, so to come up with 30 pound per feet. And then for the black wall, this was derived in terms of gamma now, 105 pounds per cubic feet times 8 by 1. Okay, where is 1 here? Because 12 inches is equivalent to 1 foot. So we would like to reiterate here that we should be consistent in our units, especially in multiplying terms. You cannot directly multiply two variables of different units. Okay, so we take note here that the unit is per foot. Okay, so to have an explanation to that, okay, concrete slab, where it came from. Actually, this is the concrete slab. Let us just place an imaginary dimension here, say that is L. Okay, so it was derived through this criteria: floor fill, lightweight concrete plane per inch millimeter. So in PSF, remember PSF is a pressure, 8. So that is 8. Okay, so the first step that we have learned a while ago, perhaps we can convert this pressure into force. How to do that? Just multiply it by the area times thickness in terms of gamma. Okay, so force is equal to gamma times 6L times 4. So 8, although 8 is pressure, 8 PSF is a pressure, we note that this was derived through gamma. That is why I am placing here an imaginary L for you to understand that one. So what is the volume? So we are actually deriving this slab here. Okay, 6 times L times 4. Now you might ask, why is it that I have directly multiplied 4 here, not converting it to a certain feet unit? Because in this table, 8 is PSF per inch. PSF per inch, so that you can directly multiply an inch unit for the thickness. So again, force is equal to 192 L, and then the uniformly distributed load now is W is equal to force all over the length. We wanted this to distribute on this length, so the divider is L. So 192 L all over L. L here is cancelled. Therefore, the answer is 192 pounds per feet. That is why we have pounds per feet. So for further understanding, you might ask, this is a scenario wherein I would like to show that table 1-3 was derived out of table 1-2. So in the floor field, the intention here is we just wanted to have a shortcut that we just multiply it by the thickness in order to have an immediate calculation of the weight in terms of inches. But it is derived out of the minimum densities or table 1-2. So as we can see here, concrete plain cylinder, we find it also cinder concrete per inch. So the original one is 108. Okay, 108. So the derive was 9 PSF. Actually, it came from the relationship between the pressure and the gamma. Okay, so we have discussed that pressure is equal to gamma times thickness or height. So in this case, the gamma is 108. And then, what is the thickness? 1/12. Why is it that 1/12? Because this 108 here is pounds per cubic feet. We wanted to express a thickness that is in terms of feet also. But in table 1-3, we wanted to express it in terms of inch. Therefore, 1 inch is equal to 12, or 1 foot is equal to 12 inches. So multiplying that, actually that is dividing 108 divided by 12 is 9 PSF per inch, which was present in table 1-3. And similarly, for plain stone concrete, 144 divided by 12, that is 12 PSF per inch, which is in table 1-3. So we have used here lightweight concrete in between, that is 8. Actually, that is missing here in table 1-2. That is missing in table 1-2. But if we wanted to compute that, just reverse this procedure. Okay, we just reverse that procedure. The pressure is equal to gamma thickness or height. The pressure here is 8, right? 8 PSF per inches. And then this is the gamma, 1/12. Then the gamma for a lightweight concrete should be 96 PSF, which is not present here. However, we can actually derive that by that procedure. Okay, so moving on, that's it for concrete slab, 192 pounds per feet. Moving on to plaster ceiling. Plaster ceiling, where's that? Table 1-3. They have used again PSF, plaster on tile or concrete, pounds per square foot. What is the square foot covered by this plastered ceiling? This actually 6 by L, right? So 5 times 6 by L, that is 30 L, and then distribution W, or distributed load force per length, 30 L all over L. So in short, that is 30, or L here will just be cancelled. 30 pounds per feet, as simple as that. So don't be confused with that. Okay, so moving on to the black wall. So the black wall was searched on the table 1-3 in terms of pounds per cubic foot. We have here masonry lightweight solid concrete, that is 105 pounds per cubic feet. Here we have the volume. What is the length? L. The width is 12 and the height is 8 feet. So remember that 12 here is in terms of inches, and we have to comply with the cubic feet strictly. That is why we have 105 L times 12. This is 12, but we should convert that into feet, okay, and then multiply it by the height 8. Therefore we have here 840 L. Again, distributing that along the length, we divide it by the length, or 840 L all over L. L will just be cancelled here to come up with 840. To sum up that one, we have 1062 pounds per feet, the distribution along the length, along this length. Okay, so that's the explanation there. So moving on, this is another type of loading. This is live loads. Live loads can vary both in their magnitude. So this is according to the RC Hibeler. Live loads can vary both in their magnitude and location. They may be caused by the weights of objects temporarily placed on a structure, whether moving vehicles or natural forces. So in NSCP, live loads are those loads produced by the use and occupancy of the building or other structure, and do not include dead load, construction load, or environmental load. So for the Merriam-Webster, the load to which a structure is subjected in addition to its own weight. So opposite to the dead load, the key term for the dead load is a permanent items that are attached to the building. Live loads are moving loads or not temporary in nature. So like classroom, there are times that live loads varies in a classroom depending on the size of the people going in and out of the classroom, or perhaps according to its occupancy, like hardware. A hardware have greater live load comparing to residential, of course. Okay, so all of those were derived on the codes that was introduced to you. Okay, so how did they derive it? So it is through calculations and experimental derivations. Okay, so in ASCE, there are live loads here according to occupancy or use. So you can see we have live loads for assembly areas, chatters. If we have a fixed seats, we have 2.87, and if we have movable seats, it will be larger than that of fixed seats. Also, we have garages, office buildings, lobbies, offices, light, heavy, storage, warehouse, residential, whether private or public, schools, and then we have a larger factor for or a larger live load for the corridor. So perhaps the primary reason why is it that the corridors have a larger value, simply because they considered the impact loads during the occupancy of the corridor, because in a certain condition, there are common times that these corridors are more utilized than that of classrooms. So again, aside from ASCE reference, we have also live loads derived from the National Structural Code of the Philippines. Okay, moving on. We have live load reduction. So for some types of building having very large floor areas, many codes will allow a reduction in the uniform live load for a floor. For the reason, it is unlikely that the prescribed live load will occur simultaneously throughout the entire structure at any one time. So for a larger structure, the code permits a reduction because the reason for that one is hindi mapupuno yung building ng sabay-sabay because of the large area. However, you can reduce a certain live load. However, the limit is KLL times 80. The limit should be 400 square foot or 37.2 square meter or more. But a certain value lower than this limit, we cannot reduce, or the live load reduction is restricted. Okay, for the reduction, L here is already the reduced design live load per square foot or square meter. That is why we have a two formula here for English and SI units. So LO is the unreduced design live load per square foot or square meter. See table 1-4. KLL live load element factor for interior column. KLL is equal to 4. And then 80 here is the tributary area in square meter. Okay. So again, we would like to emphasize that the reduced live load should not be less than 50%, nor not less than 40% of the original live load. Say for example, the original live load is 1. It cannot be that 1 is reduced by 0.49 for a building that is supporting one floor. Okay, so it is also not allowed that 1 could be reduced to 0.44 for members supporting more than one floor. So that's the limit. So your original load could not be reduced more than 50% for one floor, or it could not be reduced more than 60% for members more than one floor. And no reduction as well is allowed for loads exceeding 400 pounds per foot squared or PSF, or 4.79 kilonewton per square meter in English or SI unit. Okay, so I think this is the limit. We should not reduce if the values is equal or greater than this value. However, if we have less than these values, we can reduce the live load. So as for the table, we have here called from ACI 318-19, we have live load element factor, KLL, that is present here in the formula, as well as the checking of the influence area, KLL80, this one. If we have an interior column, our KLL factor is 4, and then exterior columns without cantilever slab 4, edge columns with cantilever slab 3, corner columns with cantilever slab, edge beams without cantilever slab, interior beams, and then all other members not identified, including this one. Okay, so let us now have an example. So a two-story office building shown in the photo has interior columns that are spaced 22 feet apart in two perpendicular directions. If the roof loading is 20 pounds per square foot, determine the reduced live load supported by a typical interior column located at the ground level. As we can see here, the tributary area are the half dimension or the half location of the nearest adjacent area carried by this column. So if this is 22, the tributary boundary here is 11 on this side and also 11 on the other side. Similarly here, 11 on this side and 11 on this side. Because of symmetry, just the same, it will yield to 22 both directions. So, as shown in the figure 1-9, each interior column has a tributary area or effective area of 22 by 22, or that is equivalent to 484 square foot. So a ground floor column therefore supports a roof live load of, we have here the roof live load 20 pounds. Where this value came from? 20 pounds per square foot. Is the roof loading here, 20 pounds per square foot. Okay, so if we derive now our KLL80, this is KLL80 or influence area, what we call influence area, that is equivalent to 4 times tributary area, right? So multiplying that is 1936 square foot. And as we recall, ASCE 7-10 allows a reduction of live load on a member having influence area of KLL80 of 400 square foot or 37.2 square meter or more. Now 1936 is greater than this value. That is why we are allowed to reduce. Okay, so going back to the live load of the roofing, this is the live load. Again, if we wanted a force, then we divide it by the area if the pressure is given, right? So we discussed that a while ago. So multiplying that by the tributary area, it will become 9,680 pounds. That is the force. So we have a notation here. It cannot be reduced since it is not a floor load. So that is the ruling that it is only the reduction is allowed on the floor load. For the second floor, the live load is taken from table 1-4, or the LO or original live load is 50 pounds per square foot. So it is a garage, as we can see on the picture. The the occupancy is a garage here on the second floor, or the second floor. So that has an equivalent live load of 50 pounds per square foot. So applying now the formula, the equation, 50 times 0.25 plus 15 all over square root of 1936. This is KLL 80, or the influence area. So let us go back to that formula here. KLL 80. Okay, 0.25 here is constant. LO is the original live load, or the unreduced live load, that is 50, coming from this table. Okay, so this is 50. This is the original or unreduced live load. This is constant 0.25, and this is KLL 80. Okay, so let us now investigate the result. So as a result, the reduced live load defined by equation 1 is limited to not less than 50% of LO for members supporting one floor, or not less than 40% of LO for members supporting more than one floor. So if we have the result here, 29.55 pounds per square foot, that is the original. We divide that by this is the reduced one. We divide that by the unreduced, and then multiply by 100% to come up with the percent unit. We have 59.1%. It is a greater value. Or by inspection alone, what is the half of 50? That is 25. And 29.55 is still greater than 25. So pasok pa rin siya sa criteria na we cannot reduce it more than 50%. Okay, so FF, or the force along the floor, is 29.55. This is now the live load. Again, this is square feet we wanted to eliminate. Multiply it by the tributary area, then we come up with the pounds, 14,300 pounds, or that is equivalent to 14.3 kips, because 1 kips is 1,000 pounds. So we now sum up the roof force as well as the floor force. So all in all, we have 24 kips. So this is the answer. So next, we proceed to highway bridge loads. So there are criteria based on the heaviest truck load on the traffic. So ano ba yung heaviest on the traffic? It is truck loadings. So for design specification, we just refer to ASCE LRFD bridge design specification. Okay, so highway bridge loads. So highway bridge loads, the concept is that each varies from 20 tons to 30 tons. It depends on each series of the truck year specification, which is where it is reported. So H here is denoted for double axle. So double axle. So this is a double axle usually present in the rear portions of the truck. That is why this the whole H is being considered. Now the wheel here is a single one, because H now is derived on 2 axles, then we divide it by 2, because this is a single wheel axle in front. So that is the concept. So for the railroad bridge loads, specifications for steel highway bridges published by AREA, or the American Railroad Engineers Association. So first we have E-loads that was devised by by Theodore Cooper in 1894, and then eventually it was evolved by Steinman, has updated this Cooper's load distribution, and now came up with M loadings, which are currently acceptable for design. Since train loadings involve a complicated series of concentrated forces, so perhaps the procedure is tedious when it comes to train loadings. Therefore, it was simplified by the established tables and graphs and influence line to obtain critical load. Also, computer programs are used for this purpose. So later on we will learn how to construct also influence line when it comes to moving loads. That procedure usually simplifies the tedious analysis when it comes to complicated series of concentrated loads. Anyway, nowadays we have a lot of power programs, okay, computer programs, powerful computer programs for this purpose. Okay, so impact loads is another type of loading. Usually these are applied in bridges wherein moving vehicles may tend to bounce or sidesway as they move over a bridge, and therefore they impart an impact to the deck. So the percentage increase of the live loads due to the impact is called the impact factor I. This factor is generally obtained from formulas developed from experimental evidence. So the impact load formula is this one. I is equal to 50 all over L plus 125, but not greater than 0.3. Okay, so here another type of loading, of course, wind loads. So this is derived, the procedure was introduced by this American Society of Civil Engineers, wherein the wind's kinetic energy will be transformed into potential energy of pressure that causes wind load to a certain structure. So the permitted design methods there are 3 methods for permitted design. We have method 1, or design methods. There are 3. We have method 1, simplified procedure. This is according to 7-05 section 6.4. So low-rise buildings, this is an outgrowth of work done by the metal building industry. And then method 2, the analytical procedure. This is the typically used procedure, the common procedure that is used in deriving wind loads. This is the main focus of this presentation. And then method 3, the wind tunnel procedure. So this is in accordance with ASCE 7-05 6.6. So titingnan natin, magkakatabi lang tong mga basis or according to ASCE. So in wind load there are exposure categories. We have exposure A. Actually this was already omitted in the latest version of ASCE. Exposure B, urban and suburban areas, wooded areas, areas with many closely spaced obstructions. Exposure C, open terrain with scattered obstructions, airports, areas that are generally flat, open country. Exposure D, flat, unobstructed areas, and water surface outside hurricane-prone regions. This category includes smooth mud flats, salt flats, and unbroken ice that extend to 5,000 feet or 20 times the building height in the upwind direction. Okay, so this is the latest criteria here. ASCE 7-10. These are the formula. We have QZ is equal to 0.00256 multiplied by a series of factors like KZ, KZT, KD, and the velocity. Okay, so this is in English, and this formula is for SI units. So for the definition of each of the variables, KZ is the velocity pressure exposure coefficient, which is a function of height and depends upon the ground terrain. Table 1-5 lists values for a structure which is located in open terrain with scattered low-lying obstructions. And then we have also here KZT, a factor that accounts for wind speed increases due to hills and escarpments. For a flat ground, KZT is 1.0. So whenever there is a flat ground, of course, there is less obstruction or to block the entry of the wind in your structure. That is why for flat ground, KZT is set into 1 because there is no other obstruction to block further the entry of wind directly into your structure. So now KD is a factor that accounts for the direction of the wind. It is only used when the structure is subjected to combinations of load. For wind acting alone, KD is equal to 1.0. Okay, so take note of that. If the wind load is not combined with any other loading, then set KD is equal to 1.0. Now, V is the velocity in miles or miles per hour or meter per second of a 3-second gust of wind measured 10 meters above the ground. Specific values depend upon the category of the structure obtained from a wind map. Okay, depending on the location, of course, there are variations on the values of the velocity. Actually, in NSCP, it provides Philippines wind map. As we can see here, we are somewhere here. So basically, our wind line here is around 200 plus. So closer to the Sierra Madre Mountains, we have 300 meter per second velocity. Okay, so ASCE 7-10 provides tables for these values. Okay, KZ, velocity pressure exposure coefficient for terrain with low-lying obstructions. So as we can see here, depending on the mean height of the structure, whether on feet or meters, there are derived values for the KZ. Okay, so this is the first variable or the first factor here. However, if we do not have any available distance within this table, we are going to interpolate values of Z in order to come up with the value of Kz. Okay, and then the next variable is Kzt, and then Kzt is equal to 1 plus K1 plus K2 plus K3, that is squared. And the values for that we have here, table 207A 8-1 by the NSCP, depending on the ridge scarp axis symmetry. Okay, this is X all over LH, 2D all other cases. So these are the multiplier. So H is the height of the hill, LH is the distance upwind to the crest, where the difference in the ground elevation is half the height of the hill or escarpment in meters. Actually, here is the diagram. This is the LH, this is H over 2, this is H. If we have a 2D or 3D axis symmetrical hill, we have also that label. So I think this is quite similar. Okay, so if we have this as the inclination, let us just divide that by 2. Okay, the horizontal distance caused by this inclined distance is LH, and then we have H over 2, and total is H. Okay, for wind directionality factor, of course it is also present in the National Structural Code of the Philippines, KD. We have totally enclosed, we have KD 0.85, or main wind force resisting system 0.85, and among others here. Okay, so for the design wind pressure is equal to this one, Q, wherein the Q that will be derived, and then QH is derived from QZ a while ago, multiplied by GCPI, and then Q here is multiplied by GCP. Okay, so we take note of the variables here. P is QGCP minus QH times GCPI. Q, what is Q? The derived QZ a while ago. For the formula for that, for the windward wall at height Z above the ground, equation 1-2, and Q also is QH for the leeward walls, side walls, and roof, where Z is equal to H, the mean height of the roof. And then we have G as the gas effect factor, CP is roof pressure coefficient determined from the table. Okay, GCPI, the internal pressure coefficient, which depends upon the type of openings in the building. If your building is fully enclosed, then GCPI is plus or minus 0.18. So why is it that plus or minus? It's simply because if we have a plus that is towards the surface, or that is a pressure on the building, but the internal pressure effect also has a suction pressure, or away from the surface. So that is why plus or minus. The signs indicate that either positive or negative. When we have negative, that is a suction, or it is actually pulling the surface. So it can occur a suction and a pressure on the building or the surfaces of your building. Okay, so design pressure P, So here we have the layout. As we can see here, this is the top view. If we have a ridge here, this is the top view. If this is the direction of the wind, this is what we call, this side is what we call the windward, and the other side is what we call the leeward. This is windward, this is leeward, and this is roof windward, and this is roof leeward. Now, with regards to CP, or wall pressure coefficients, these are the reference, or the table A will be the reference, as well as the table P for these diagonal members. So this is for the wall, and this is for the roof. Okay, so how shall we use this one? Okay, for windward wall, so this is windward wall, we'll just have to divide L over B. What is L over B? This is L, or the length parallel to the wind direction, and B is the distance perpendicular to wind direction. So there's no problem on the windward wall because it accepts all values that the CP should be 0.8, and we're gonna use that with QZ. And then leeward wall, so this is the windward wall, the other side is the leeward wall. Again, L over B, we have some values here. Okay, we have here QH as compared to this, and then side walls, all values should be negative 0.7. Okay, so on the roofing portion, the criteria is dividing the mean height. As we can see, the mean height, the total height of the column plus the half height of the king post here. It is not up to the top, but it is half of the king post here. Okay, so doing that, just investigate the value of H over L. If it is less than 0.25, then negative 0.7 is our factor. If it is 0.5, negative 0.9. If it is greater than 1, negative 1.3. Okay, for the leeward angle, these are the factors. Okay, so pressure coefficient CP, so these are more detailed, because in here, as we can see, this is just a portion of the table, because it only present 10 degree angle. So here we have a lot of angles. Okay, H over L. Okay, so this is the table that is found in NSCP, or the National Structural Code of the Philippines. So another table is the GCPI. So GCPI, totally enclosed building plus or minus 0.18, and among others we have here the GCPI. Okay, so let us consider now an example. So the enclosed building shown in the photo is used for storage purposes and is located outside of Chicago, Illinois, on open flat terrain. When the wind is directed as shown, determine the design wind pressure acting on the roof and sides of the building using ASCE 7-10 specifications. As we can see here, we note that the building is totally enclosed, and that the wind direction is perpendicular to 150. Parallel is also 150. We have here the roofing inclined at 10 degrees. 25 feet is the column height up to the bottom of the truss. Okay, so here it is. Here is the cross section. We are going to use QZGCP for this windward wall and leeward wall QHGCP. We have QHGCP for the roof windward and QHGCP for the roof leeward. So we are going to use obviously English here because all of the units are in terms of pounds and feet. So let us have the first variable kz. So we need to know what is h so that we can derive kz. What is h here? The mean height, as I have said, that is the sum of the L or the height here plus the half of the height of the king post. Okay, so let us have here the derivation. Mean height is the 25 here plus x over 2. What is x here? X is the total distance up to the top. So half of that is the needed distance included in the mean height. Now x is a function of the tangent. 10 degrees is equal to x all over 75 because this is 75. So utilizing this right triangle, okay, so x therefore is 75 tangent 10, 13.22, and x over 2 is 13.22 all over 2, that is 6.61 feet. So moving on, just substitute here, then our mean height would be equal to 31.61 feet. So why did we get that mean height? Again, we need it on the table, but in the table you cannot find there 31, right? It is in between 30 and 40. So we will derive the mean or the kz by its interpolation. Okay, so the step is we're gonna pick the boundary between or the lower limit of 31. The nearest to 31 is 30, of course, and the upper limit of 31, the nearest, is 40. Okay, so we're going to have a line there, and then 30 is being paired to this 31.61, and 30 is being paired by the upper limit, lower limit to upper limit, and then lower limit to the value wanted to interpolate. Similarly, in kz, of course, we will delegate the unknown kz for 31.61 as a variable, that is x. Similarly, we are going to connect lower limit and upper limit, and lower limit as well as the variable. Okay, so doing that, we can say that first we have here this one 31.61 minus 30, and then the other side we have x minus 0.98. okay, and then we have here 40 minus 30, and then 1.04 minus 0.98. Solving for x is 0.989, or the corresponding kz for 31.61 is equivalent to 0.989. Okay, so we have derived that V. So we're going to get the other factors. QZ for a mean height of 31.61. We have this constant 0.00256. 0.989 is the KZ for 31.6 height, and then KZT is 1, KD is 1, and the velocity is 105. So KZT 1.0 for a flat terrain, that is noted in the problem. KD 1.0, since we are just concerned with the wind load, it is not combined with any other loading. And V here is 105 miles per hour based from the wind map. In Chicago, Illinois, the velocity is 105 miles per hour. Okay, so substituting the values, we will come up with 27.9 PSF, pounds per square foot. So that is the value for QZ. Okay, so let us now derive for the corresponding pressure. So QZ for a mean height of 0 to 15 feet, we have here 0.85. 0 to 15, we have KZ of 0.85. So we'll just replace that in the formula, and then we have 23.99 PSF. So we also wanted to compute for the QZ for a mean height of 20 feet. 20 feet has KZ of 0.9, so we'll just replace the value of QZ for 20 feet. We have 25.4 pounds per square feet. Finally, we have QZ for a mean height of 25 feet has a corresponding KZ of 0.94. Then we have 26.53 PSF. As a summary, if we have a Z of 0 to 0.15, we have KZ 0.85. These are the corresponding values, okay, that we have computed. Where shall we use that one? It will be used here in the computation of the pressure. So the wind load calculation or the pressure calculation consists of QGCPI, QHGCPI. So GCPI is plus or minus 0.18 for enclosed buildings, and the G here, or gustiness factor, is 0.85 since it is a rigid structure. Okay, so we'll now proceed to the windward wall. So where is the windward wall? So this is the windward. So if this is the direction of the wind, the side nearest to it, or the direct hit of the side, will be the windward. So this is the windward wall. And then windward wall, L over B, we do not need to compute that one because all values are accepted to have a CP of 0.8. So here, okay. So after getting that CP is equal to 0.8, we will have a substitution. So first, we computed the windward wall, or the windward wall. Here is the side of that. As we can see in the graph, it turns out to have decreasing up to the bottom. Why is it? Because we have different height from 0 to 15, from 20, from 25 up to 31.61, as we have computed a while ago. Okay, so for a mean height of 25, we have a mean height of 20, 0 to 15, and the first one up to the 31.61 feet. That is why this is not constant here. There will be a curve here. Okay, so let us compute the value here. So first we have 0 to 15. We have already derived the Q under 23.99 a while ago. Okay, and then the G is gastiness factor 0.85 for rigid structure, and then 0.8 was derived as our CP, then minus 27.9. So 27.9 here is the value of Q at 31.61, and then multiplied by plus or minus 0.18 as GCPI. Okay, so substituting the values, then we will be having an upper limit of 21.33 PSF and 11.29 PSF for a windward wall at 0 to 15 feet. So this is the upper limit and this is the lower limit. So meaning we will be having a two sets of loading here. That is for the wind wall for 0 to 15 feet. And then windward wall at 20 feet. Okay. So this is P20. Again, the same formula. So we have derived the Q for a height of 20 feet, that is 25.4, and then the same factors here, the same Q here at 31.61, the same QGCPI. Then we have an upper limit and lower limit again, okay, for that one. So next to 20 is 25. A similar procedure was employed. Q computed a while ago is 26.53 for a height of 25 feet. Okay, the same factor for GCP 0.85 and 0.8. The same QH is actually the QZ at 31.61 plus or minus 0.18 the value of GCPI. Then we will yield to this upper limit 23.06 PSF and the lower limit 13.02 PSF. Okay, that's it for we are done with the windward wall. For the other side, that is the leeward wall. So on this table, we need to derive L over B to locate what is the appropriate factor CP here. Okay, so what is L? L here is this one, or the distance parallel to the wind, and this is the distance perpendicular to the wind. So eventually 2 times 75 all over 150 is equal to 1. So L over B is equivalent to 1. So looking at the table here, it falls under this first leeward wall, that is negative 0.5 as its CP. Okay, so take note of that. So again, we will just substitute. So if we investigate now, the Q here is the minimum or the maximum Q computed when the height is 31.61. So it will be similar to the Q here. and the Q there. Okay, and then 0.85, we'll just replace the CP here, negative 0.5, and then we will come up with these values, negative 16.88 and negative 6.84 as a lower limit for the leeward wall. Okay, next is the side walls. So the side walls are these sides, okay, or the sides which are parallel to the direction of the wind. Of course, it is also present in the table. We have side walls. We do not need to investigate all L over B because it is applicable to all values. Should have CP of negative 0.7. Okay, again, applying the formula, this is 27.9, this is 27.9. 0.85, we just replace this negative 0.7 plus or minus GCPI, that is 0.18. Finally, we have an upper limit of 21.62 and negative 11.58 as a lower limit. Okay, that's it for the leeward wall. We proceed now to the roofing. Okay, so this time our criteria to locate its CP is H all over L. What is H again? It is the mean height, and that is 31.61, sorry, 31.6 all over the L, the same L, 2 by 75, and that is equivalent to 0.21, and it is less than 0.25, so meaning at 10 degrees, that is negative 0.7 as its CP. So that's it. The cycle is that just we determine the variations on CP with regards to the members. Okay, again, we apply the formula. It only varies with this CP value. So it so happened that it is similar to the leeward wall here. We have an upper limit of negative 21.62 PSF and negative 11.58 PSF. Okay, so finally the leeward roof. So for the leeward roof, 0.21 is our H all over L. So this is the leeward angle, 10 degrees. Of course, this is the value. CP is equal to negative 0.3. Okay, so again, we substitute the values in the formula of pressure to come up with this upper limit and the lower limit. Okay, so it's so easy. As a summary, we have this one. We have 3 sets for this. Why 3 sets? Because it is for the value of 0, 0 to 15, 20, 25, 20, and 25. Okay. So this is the upper limit portion, and this is the lower limit portion. Okay, so that's it for the solution for that problem. And then we also have a criteria for derivation of the force. So you can see it is already force. Q is equal to QH GCF AS. So this is the CF factors. So this is the wind pressure of signages. Okay, signages. QH, the wind pressure evaluated at the mean height measured from the ground to the top of the sign. Again, G is the wind gas coefficient factor. CF is a factor coefficient which depends upon the aspect ratio, width B of the sign to the height of S of the sign, and the clear area ratio, sign height S, okay, sign height to the elevation H, measured from the ground to the top of the sign. Cases of wind directed normal to the sign and through its center for B over S is equal to 4 values are enlisted in this table. Okay, so that's it for this presentation. I hope that this should help. So kindly review the video, and I will also be uploading the PDF file of this for your reference. So thank you and have a nice day.